every time. There we go, recording. So we go right to the ratio test on this and just completely ignore the -1. This will be important in the next class or two when we do what we're doing today, but so we ignore this. So we go to the ratio test and we're looking at the limit as n goes to infinity. And these absolute value signs, that's why we can ignore the -1, because the fact that this is alternating isn't going to affect anything. So we have this one. So we're going to divide by this, which means flip and multiply. And over here, we put this down here, and each of these n's get replaced by n+1. So we get 2 to the n+1, and on the bottom, we get n+1 factorial. So it's a little bit dark in here, and I don't know how to get rid of this like beam from heaven over here. But can you see that okay?
I can see it.
Okay. Well, it's your question. You're the only one that matters, so that's all. All right. So now we do a little bit of algebra stuff here. So this 2 to the n+1, that's just 2 to the n times 2. And so this 2 to the n and that 2 to the n are going to cancel out. So we'll get limit n goes to infinity. And that will leave me with a 2 up on the top, an n factorial over n+1 factorial. Oh, wait a minute, here comes somebody coming in. Just a second. So, okay, so far, Cassidy?
Yeah, I didn't get rid of the -1, so then it messed everything up. But that makes more sense why you get rid of it.
Yeah, well, it'll still work if you don't get rid of the -1, but it really looks awful, doesn't it?
Yeah.
Yeah, so that all goes away. So that was your problem. You just made it look pretty ugly. So this n factorial and n+1 factorial, they cancel out, sort of. So this n factorial, so n+1 factorial, the next term would be n factorial. So that cancels out with that. And that leaves us with 2 over n+1. Now as n goes to infinity, the denominator goes to infinity, constant on top, so the whole thing goes to 0. And 0 is less than 1, so the answer to this is converge. Yeah, so when you leave the -1 in, it'll all still work out, but it just kind of gets ugly.
Okay, thank you.
If you had left that in there, you would have been left with a -1 inside here. And that wouldn't affect the fact that the denominator still goes to infinity. So that was actually a pretty good question that you asked, because when we do what we're going to do towards the end of the class today, that negative is going to come back for other reasons on there. So that was a good warm-up after being off for a whole week. Does anybody else have any questions? Ratio test. Daniel, number 59, we sure can. So number 59. Okay, so number 59 out of the homework is out of a batch of not necessarily ratio tests, just a bunch of things, and you got to figure out if they converge or not. And that's where the thinking comes in. Kenneth and I were talking earlier. The series things can take some thinking. So number 59 is, boy, I really got to get some glasses here. So we have infinite series. We're starting at n equals 1, and we get 10 times n plus 3 over n 2 to the n. All right, there we go. Now, as n goes to infinity, this 2 to the n power is going to get really big really fast. And the top is just going to kind of plod along here a little bit. So what's going to happen here, we can use the ratio test on this one, as a matter of fact. So let's try that one. So here's one of the things to think about. when you have an n factorial, or when you have an n that shows up as an exponent, an exponential, ratio test is probably a good thing to do. So if we go to the ratio test, we get the limit as n goes to infinity. Now here we don't need absolute value signs because there's no negatives up here and we're starting at 1, but it's a good idea just to get into the habit of it. So over here, we'll have n 2 to the n over 10 times n plus 3. And over here, all the n's get replaced by that. So we'll have 10 times n plus 1 plus 3 over n plus 1, 2 to the n plus 1. And the reason I'm flipping that in, when you do the ratio test, you get n plus 1 over a n. So that's the general form for the ratio test. But when you divide a fraction by a fraction, you just flip it. So that's the reason I'm writing them this way. So now a whole bunch of stuff is going to cancel out. So up here, 10 times n plus 1 plus 3, this will turn into 10n plus 13. Now, so these are all just going to cancel out because this is n to the first, and this is n to the first. And the 13 and the 3 don't mean anything when we go to infinity. So these, this is where I wish I had a much larger, boy, that, I don't know how to get, that glare is really, hang on just a second here. Let me see if I can get rid of this. Hold on. Oh, look at that. Is that better? Oh, no, that's worse. Let me see if I can fix that. Oh, well, that's a little bit better, I guess. Okay, where was I here? Oh, so these will cancel out because n to the first, it goes away. And that will leave us with this n and this n plus 1. So as n goes to infinity, this plus 1 doesn't mean anything. So these will also cancel out. And that will leave us with 2 to the n over 2 to the n plus 1. And 2 to the n plus 1 becomes 2 times 2n to the first. And now the two n's cancel out. And that will leave us with just 1 over 2. So this whole thing equals 1/2. And since 1/2 is less than 1, this converges. So that's a lot of messy looking board there. But Daniel, did that make sense?
I got completely lost in that last step. Can you redo that for me, please?
This last step here?
Yeah, like with the canceling out.
Oh, okay. So looking at the red, all right, just looking at the red here. Let me go up here. Get this, yeah. It's the effect of having a tiny whiteboard. So looking at those the red cancellation here, we have 10 times n plus 13 over 10 times n plus 3. So that's what this canceling out is. Now, as we go to infinity, the 3 and the 13 mean absolutely nothing. And so this just all cancels out and just equals the number 1. So that's what it means to cancel out. I didn't think the n plus, and where's n plus infinity? N plus infinity, not sure what you mean there, Daniel. N plus infinity, you're not really sure what you meant by that. So the red things cancel out. And then that leaves us with an n and an n plus 1 in green. So in green we have, n over, oh, it doesn't show through. That's not showing through. So in the green we have n over n plus 1. And that just goes to 1 as you go to infinity. Any constant here isn't going to matter. So n to the first over n to the first cancels out, and that just means becomes 1. And so that left us with just the 2's here in the 1/2. The whiteboard's really small in this, but did that help a little bit, John?
A little bit, yeah. But then how did you end up with the 1/2?
Oh, that's the easy part. So hang on, that's just lost in the messiness here. So we ended up with this, and when all that went away, we ended up with the limit, n goes to infinity, of 2 to the n over 2 to the n plus 1. But 2 to the n plus 1 is 2 to the n times 2. So I broke up the exponents here. So the 2 to the n's cancel out, and that just leaves me with 1/2. So it's a little bit messy. Let me make a note. When I send out the homework for tonight, I'll include more, I'll redo this problem with more writing and explanation. That might make it better. So if you can hold off, I'll send out a more detailed explanation about that. Because it's just too cramped on this whiteboard here. Hang on a minute. I'm going to make a note to myself to do that. What was this? Number 59, right? Yeah. Okay, I'll send you out like a whole detailed explanation on it so it'll make more sense. All right, anything else? Okay, so let's do something brand new for today. So what we're going to do today is power series. This is section 9.8. Let me get a marker that works better here. So power series looks like this. Here's the general definition. So that's a basic, where am I here? Wait a minute. Let me use the same notation as they use here, so I don't confuse you. And we'll start at 0. Now, right now, that's just sort of a generic infinite series. With a power series, though, we're now going to make it a function of x. So we're going to introduce the variable x into here. So parentheses, x minus c to the n power. That's the definition of a power series. So I'll write out the first few terms here. So we have n equals 0, n equals 1, n equals 2, n equals 3. So when n is 0, we get a sub 0, and to the 0 power, this just becomes 1, plus a sub 1, x minus c, plus a sub 2, x minus c squared. Well, I can only go up to 2 here. So it looks like that. All right. So this x minus c is also getting exponents. So exponent of 0, exponent of 1, exponent of 2, exponent of 3, and so on. So this is what a power series looks like. And these are now a function of x. But in this series, the n's are the only thing that are changing. That x stays x all the time. The x itself isn't changing. And this is essentially, you're going to see today how your calculator does sines and cosines and e to the x and all of that. So it becomes a function of this. Now, all power series converge. All power series converge depending on we can make every power series, we can make it converge because we get to choose the value of x. So by picking appropriate values of x, we can always make a power series converge. Our job today is going to be to figure out what are those values of x that will make this power series converge. And we are in section 9.8 in this thing here. So that's the general definition. So I'm going to go through a little bit more of how this concept works. So hang on. Let me get rid of this. It's from yesterday. Okay. So every power series can be made to converge by the appropriate choice of x values, and it will happen in exactly one way. So let me pull this other board back up here for just a second. In this expression, in the expression x minus c to the n power, this part right here, c, this constant, c is a constant, and c is the center. The letter C stands for center. So when we're picking x values, we're picking a value off of the x-axis, the x number line, and the C is the center. So one of the ways is converges at only at the center. So this is the x-axis here. So we pick the value of C, let me write over here. So if, to the n, if x is equal to C, if x is equal to C, what does this expression become? If we let x equal C, what does all of this equal? 0. Yeah, Kat, you got it. Then x minus C to the n is equal to 0. And so your infinite series just becomes 0 plus 0 plus 0 plus 0 plus 0, and it converges. Okay, but that's not a very interesting power series. It only converges there. for any other value of x, it will diverge. So one way is only at the center. And this will make sense in a little bit. The second possibility is a finite radius and that would look like this. So here's the center. And this would be C minus R. And over here would be C plus R. So we have this radius on here. And from the center, you add the radius. And so here, all x values in that interval, all of them, will make this power series converge. And this will all make sense in a minute when we do some examples here. And the third one is everywhere. And that means any value of x will make it go. And so it would be like this. Here's the C, here's positive infinity. So the third thing is any x on the number line, all of them make it converge. So three possibilities, only one value of x, the value of the center, a finite number of x's, well, a finite interval in here, where all the x values in between will make it converge. X values outside of that window will make it diverge. And the other possibility is any x on the number line will make it converge. So this will make more sense in just a second here. So we're going to go kind of slow on this. This is a very important concept. This is how, well, this is how computers calculate a whole bunch of things. And I'll show you in a while what e to the x looks like. All right, so let's do an example. And for this first example, I will take, let's see here. Where am I? Lost, oh, there we go. So this is example number 8. And I am on page 654. And here's the power series. So n equals 0. And we have -1 to the n. And on the top, we have x to the n. And on the bottom, we have 5 to the n. So here's our power series. Now, in this case, here's the general description. So that's the generic power series here. So in this case, we just see a plain old x. So x to the n, we can think of this as x minus 0 to the n. So with a 0, that just kind of disappears and we're just left with an x. So on this particular problem, the center is 0 because I don't see x minus something in parentheses. So the center of this is 0, which is what a lot of them are till you get to differential equations. Okay, so we can choose this. We can choose values of x that make this converge. So we go right to the ratio test. Every time we do a power series, we go right to the ratio test. So we get the limit as n goes to infinity. Now, absolute value sign, so I'm going to ignore this for now. And that will give us x to the n plus 1 over 5 to the n plus 1 divided by this. But when we divide by this, we flip it and multiply. Like that. All right, so I'm going to pause there for a second. See if anybody's got a question. Now, a whole bunch of stuff's going to cancel out. 5 to the n plus 1 is 5 to the n times 5 to the first. And x to the n plus 1 is x to the n times x to the first, which is kind of what happened on the last question there a little bit. So this now gives us the limit as n goes to infinity. And after everything is canceled out, well, what are we left with when everything's canceled out? The x to the n's cancel out, the 5n's canceled out, and so I'm left with x over 5. Oh, Kat and Jonathan. Oh, I should have turned my head earlier. Yeah, you guys got it. Good. I guess that means my handwriting was sort of okay on this problem. All right, so that leaves it with this. Now, here's the difference of what we did before. You're always going to be left with an x in a power series. You're always going to be left with an x to the first. It's just the way these work out. And Jonathan, you're saying diverges INIT? I'm not sure what you wrote there. Oh, so what did you mean to say? Well, we don't know yet. So here's the thing, we have the ratio test. So let's go back and do a quick thing from the ratio test. Ratio test. We get the limit, n goes to infinity, of an plus 1 over a sub n. Now, if this is less than 1, we converge. For the ratio test to converge, the end result of this has to be you are less than 1. So, because we have an x, we can pick any x values we want. Oh, there we go. Infinity over. So we can force this to converge by choosing the appropriate values of x. So what we need, here's what we want. We want this to be less than 1. So we can do that, right? We can do that on here. Now I'm going to have to erase some stuff here. So before I do that, anybody have a, not n, yeah, not n, Jonathan. It's not n less than 5. There's no n here. It's an x. But you're on the right track. You thought x was n. No, x is x and n is n. So Harris, in the original problem, these are n's. They're the ones going to infinity. So 5 to the first, 5 to the second, 5 to the third, 5 to the fourth, all the way out. The x is a completely separate variable in here. So the x is its own variable. So here's how we can do this. Yes, Jonathan, you've got it. Almost. There's a little bit more to it than that. So what we have here now, here's where the absolute values come back again. This can be positive or negative because of this. So from here, we know that so all of this puts me over here. We need x over 5, the absolute value of x over 5, to be less than 1. And so here's what we need for convergence. So now multiply both sides by 5, and we get negative 5 x and 5. So this series will converge for any x value that is between -5 and 5. And it's very important that there's no or equals to here. Can't equal 5. If x is equal to 5, we get 1. We don't get less than 1. If x is -5, we don't get less than 1. We'd still be on there. So exactly, Brandon, we're forcing it to converge by appropriate choices of x. And that sentence right there that Brandon just said, well, question, you could replace the question mark with a period. We're forcing it to converge by correct choices of x. And a power series, since we can always choose the value of x, we can always force them to converge. And this has lots of implications in engineering and mechanical and chemical and all kinds of things on here. All right. So now I'm going to draw you a partial picture of the solution. Our center is 0. So right there is the center. And up here is +5, and down here is -5. And oh, look, the center is right in the center, which is why it's called the center. So we converge so everywhere in between, and so curvy brackets mean so all of these x values, we converge, right? Outside the interval, all of these x values, we diverge. So in this case, the x values which cause us to converge are a finite closed, or an interval on the x-axis. And so we have the convergence, the radius of convergence is 5. So pick any x value here. This series will add up to something. What it adds up to isn't important. Pick an x value from red, and this will shoot off to positive or negative infinity. It won't converge at all. So what's the importance of all of this? Well, let me give you an example of one way that this might be. Let me give you a stupid example. So I'm holding a pencil here, right? So I can bend this pencil. Right now, the pencil's nice and straight. If I put positive pressure on, I can bend it down a little bit. If I put negative pressure on, I can bend it up a little bit. You might not be able to see that, but you see the pencil's bending a little bit. So what happens if I put, so right now there's 0 pressure on that pencil, and that pencil is stable. If I start putting increasing pressure on it, eventually what's going to happen? It's going to snap. So as I start putting increasing pressure on here, more and more and more and more, it's going to get to a point where it snaps. And you can think of that snapping as the pressure shooting off to infinity and diverging. So positive, negative pressure, back and forth, back and forth. So if you're an engineer and you're designing a wing on a space shuttle or something, you have to know what are your tolerances for pressure. Sort of, you can think of maybe positive as upward pressure and negative as downward pressure. This would be the amount of stress that wing can handle before it snaps. So that's kind of an example of why power series are so important, right? It is interesting, Kat. I'm glad that you find it so. And the same thing happens. So the easiest thing to think of is a mechanical example. Or take a potato chip. You can bend a potato chip a little bit, but eventually it snaps. That would be the analogy to diverge. And so we can think in the center, like there's no pressure, and then you put a little bit on there. So I'm assuming most of you have flown on a commercial jet or something at some point. You look out, if you look out the window of the wings, you'll see them like bouncing. And so the wings are like bending and bouncing. They're made to do that to be able to handle turbulence. But if you exceed the tolerance for which that airplane is designed, like you bank too steeply or turn too sharply, you can snap it. So these power series have very immediate usefulness in the real world. So the answer to this homework problem, by the way, is that picture. So your answers are going to be pictures. Oh, but wait, we're not done yet. There's something else that we have to consider here. But before I do the something else, got a question about anything? I know that was a whole lot all at once. This was your first one, so it's a little confusing, right? So here's a case where the ratio test, up until now, we've been ignoring that. Now the negative comes back in. So we got a question about anything here yet? All right, but we're not done yet. There's something else that has to be considered. So we have to be careful here. So we know that we're in the red, we diverge. For x values, so for x values over here, these x values are less than -5. These x values are greater than +5. The blue ones are between -5 and +5. What's getting left out? Oh yeah, very nice, Kat. Let me get a different colored marker. Hold on. Yeah, what actually happens at 5? We converge when we're in between -5 and 5. We diverge beyond +5 and beyond -5. But what happens when we're at 5? So to a mechanical engineers, when you're bending that wing, why does it snap at that particular pressure point? Why not one that's a little bigger or smaller? What is it about that number? What is it about those precise numbers that suddenly go from converge to diverge? So here you're a stable system. Here you're an out of control chaotic system. Why that number? Now here it doesn't matter, there's no context. But in engineering, or if you're doing like a biochemical study, why does this dose of medication cure you and a little bit bigger dose kill you? What's going on with there? Well, we're going to figure out what happens. So undefined. Well, we're going to find out what happens, Brandon. So this is called the endpoints. So 5 and -5. What we need to do is look at the endpoint behavior. And the endpoint refers to the end of the interval here. So what's happening right at that specific moment? Two things can happen. A power series can converge at the endpoint value or diverge at the endpoint value. So it's possible to converge here and converge here. It's possible to diverge at both of these numbers, or it's possible to have a converge diverge at one or the other on here. So before I show you the mathematics of what we're going to do this, let me give you a little thought, a little thinking experiment here. Let's suppose we have a container of pure water. And by pure water, I mean exactly pure water. The only thing in this container, the only thing in here are H2O. Is it possible to ever have a container of pure water? Can you ever have a container of exactly pure water? No, you can't. There's always going to be stuff in it, things from the air. You can purify water all you want. There's going to be other stuff in it. There's going to be other minerals in there. There's probably some virus and bacteria in there. But we're going to pretend that we have a mathematically perfect container of water. Absolutely perfect. And other than that, it's also completely motionless. That water is absolutely still. Also not possible. But this is math. We don't care about the real world. All right, so you want to work in centigrade or Fahrenheit? What do you want to work in? Temperatures, centigrade or Fahrenheit? Oh, all right, I'll do them both. So at 0 degrees centigrade, water freezes. What's the Fahrenheit freezing point of water? 32 Fahrenheit. Centigrade, water boils at 100 degrees, and in Fahrenheit it boils at, oh, got to think about that, 212. Nice. Okay. Okay, so between 0 and 100, water is liquid. And so our water is perfect H2O and perfectly not moving. So it's the same temperature everywhere in there. Above here, it is gas or steam. And below here, it's solid. There's another one up there. There's another state of water. What's the next state of water beyond gas? Something else happens later. Turns from gas into what? Anybody know? Yeah, plasma. But it's got to be really hot for plasma up there. But anyhow, so here's my question to you. At exactly the freezing point of water, what is it? Is water solid or liquid? At exactly, yes, at exactly 32 degrees Fahrenheit, is water solid or is it liquid? Oh, it's like philosophy, isn't it? At exactly 220 degrees Fahrenheit, is water liquid or is it gas? Well, so you're right, Jonathan. It's a little bit of both in the real world. In the real world, you get this slushy kind of stuff, but that's generally because you've got other stuff in there besides water. And if water is moving, it won't freeze at 32 degrees. If the water is moving fast enough, you can get water all the way down to 20 degrees. And if it's moving fast enough, those molecules can't line up and freeze. Yeah, but we're not in the real world. We're in this mathematical laboratory where we got a container of water that's perfectly H2O and perfectly not moving. So what is it? Oh, that becomes kind of an interesting question, right? So to a researcher, engineer, or scientist, if you're studying water, you would ask yourself, what is it about the physics and the chemistry of that molecule that make it change from liquid to gas at that temperature? Why not 220? Why not 198? What is it about that specific temperature's act on that molecule that makes it have a drastic change from converging to diverging? So we can think about it that way. So to the research people, it's those endpoints that are interesting. Why there? So we have to figure out what happens at our endpoints. So to do our endpoint behavior, we have to figure out what happens to this series at this number and at this number. Does it diverge or converge? So essentially what we're going to do is plug these two numbers back in here and see what happens. So let me go to the other board so I don't have to erase this. See, I think a long time ago, I mentioned that chapter 7 and chapter 8, all the disk and washer and rectangles and do this integral by parts, trig sub, that's not really so much mathematics. That's kind of arithmetic, like moving symbols around. Chapter 9, we're getting into the more fundamental part of mathematics. We're getting into what does all of this mean and how does it work? So here's our series. And we have the so LEP is left endpoint. Our left endpoint of this interval is -5. So LEP, left endpoint. Our right endpoint, REP, is x is equal to +5. So to do our endpoint behavior, we're going to plug these numbers in and see what happens. So when we do this, we get f of -5 is equal to n equals 0 to infinity, -1 to the n, 5 to the n, -5 to the n over 5 to the n. So right now I'm just doing the left endpoint. So just plug this number, we plug it in. All right, so now I'm going to rewrite this a little bit. So I wrote this more compactly here. If you have a to the m over b to the m, just rules of exponents, you can just write it that way. So I just combined these two together. All right, so far. And now this becomes, well, this just becomes 1. You see how all of that became 1? That's going to take a little bit of thinking here. So -5 over 5 gives me -1 to the n. So -5 over 5 is -1, and they're both to the n power. So -1 to the n times -1 to the n is always going to be +1, because these are the same n, so they're odd and even at the same time. So multiplying these together is always going to give us +1. And this diverges. This series is just 1 + 1 + 1 + 1 + 1 + 1 + 1. So that diverges. So at the left endpoint, our series diverges. A lot of thinking for the first day back after that long weekend, isn't it? All right, any questions about that? All right. Let's do the same thing for the right endpoint. And I am recording this. And the book does a fairly decent job with its examples on here. So now we look at the right endpoint. And that is x is equal to positive 5. So we plug it in. And same thing, this will take us down to this. And this will all become so this whole series is going to look like this. This will always be, well, this will be an alternating series here. Not sure what the question mark is for, Kat. So this is actually going to be an alternating series because this is just equal to 1. So we just get this. Let me write it over here. So 1 to the n is just 1. So what we're going to get here is we're just going to get negative 1 to the n. And that's going to go 1 minus 1 plus 1 minus 1 plus 1. And that also diverges. It's an alternating series, and the terms are not getting smaller, so that diverges. So this is all pretty confusing for the first example, I know that. So here's the ultimate thing. Here's our result. Because of that little bit of arithmetic we just did, this series diverges at both endpoints. So that picture, the round parentheses means does not include negative 5. Round parenthesis means doesn't include that. So this picture is the answer to this problem. This power series will converge for all values of x between negative 5 and 5, and it will diverge for any other value of x. So your airplane wing that you just designed is only safe in between those numbers, whatever they might mean. So that's a lot. I'm sure your heads are spinning a little bit. I'm going to let you think about that for a minute. I got to go. I'll be right back. I got to get some more herbal tea for my throat. Okay, here I am. Has anybody got a question at this point? And don't forget, Ocean County College has hired Isaac just to be your own personal tutor in this class. And he's got his sessions that you can drop in on anytime. And sometimes it's really nice to have somebody explain something in a different way. So maybe if Isaac's explanation will be a little different than mine, and that might be just enough to get those light bulbs to turn on. So make sure you visit him. It gets kind of lonely without you guys going there. Yep, every time after class at 3. There you go. All right, now, let me show you what can happen on endpoints. Well, erase this one. So you only have endpoints. So power series will converge in exactly one way, only at their center, so there is no endpoints. The entire x-axis, the whole number line, again, no endpoints. Only when you get a finite radius of conversion do you have endpoints, left endpoint, right endpoint. So this only happens in this one instance. So here's what can happen. There are 4 possibilities. You can diverge at both endpoints. You can converge at both endpoints. That's square brackets means you can include that number. You can diverge at one, converge at the other. And the 4th possibility is just sort of the, so your endpoint behaviors are always going to look like one of those. Diverge both endpoints, converge both endpoints, diverge at one, converge at the other. Those are the only 3 things that can happen. So let's try another example. Let's see here. Let's look at, oh, I'm going to do this one. This one's sort of out in the book. Here's our next example. So x to the n over n factorial. Now in this case, there's no -1 in here. So this is just x to the n over n factorial. So we go right to the ratio test. So we have the limit as n goes to infinity. But I'm still going to draw the absolute value signs because you should just be in the habit of it. So we're going to have this, so n factorial over x to the n. Then we get x to the n plus 1 over n plus 1 factorial. So there's our ratio test. That's going to take me down to here. This looks like a lot, like a couple of the homework problems last time. All right, and that's going to give me x over n plus 1. When we get done with all the canceling, so this x to the n cancels out this x to the n and leaves me with an x on top. This is always going to happen. You're always going to be left with a single x on top. You might get some other stuff up there, but you're always going to have an x on top. And n plus 1 factorial and n factorial cancel out like this. Now, as n goes to infinity, where does all that go? Remember, only the n is moving. Even though the x is a variable, it's not changing, which sounds strange. Once you pick a value for x, it becomes a constant. So where does this go as n goes to infinity? It goes to 0. Nice. Because the denominator, it doesn't matter what your value of x is, the denominator goes to infinity, the whole thing goes to 0. So this, that converges. It does not depend. Doesn't matter what value of x you have, that's going to converge. X could be a trillion, still going to converge because the denominator is going to infinity. So this series, because of that, we're done. There's no endpoints. This series converges everywhere. And that word everywhere is a mathematical word. It means any value of x, the entire x-axis So no matter what value of x you put in there, that series converges. That problem's all done. Now, I picked this problem for a particular reason. We will next Thursday, not this, next Tuesday, I think, we're going to talk about something called Taylor and Maclaurin polynomials, power series. They are a particular kind of power series. This power series here that I've just shown you, anybody recognize that? Anybody ever seen that specific one before? Because this that's a definition of e to the x. This is how your computer does, this is how your calculator does e to the x. We can think of a series like this. This is an algorithm. This is a little computer program description. For those of you who do computer programming, this is pretty easy to do. X would be your variable, and this is just sort of an if-then. So Texas Instruments, or whoever you're using, they don't go to infinity. They might go up to 500 or something, which would give you accuracy to like 48 decimal points, which is more than any physical need. But this is the algorithm in your computer that does e to the x. So when you put in your calculator e to the x and you put in, 2.7 or 3.5 or something, it goes right here, and then they'll calculate this out to so many decimal points, and before your hand is off the enter button, it's calculated. So that is an alternate definition of e to the x. Also, there's a power series for sine and cosine, and I'm going to send you a PowerPoint tonight about how cosine and sine turn into a power series like this so that you can see it. So these powers, so infinite series, we've been doing them for a while and they've been kind of abstract. Now, all of a sudden, this is where they show up everywhere. And so it's all because of these two guys from Scotland, Taylor and Maclaurin, back in the 1700s. 300 years ago, they didn't have this notation, but they were able to take something called a transcendental function, e to the x, sine of x, cosine of x, tangent, and turn them into polynomials like this. Pretty smart. Makes our life certainly better. All right. Let's try another problem. Anybody got a question about anything yet while I'm looking for another example to do? Let's see here. Let's see. All right, just gonna make one up here a little bit. So, little example. Here's our next example. And let's have -1 to the n times x to the n. So here's our series. So it's an alternating series. When this is even or odd, this becomes negative or positive. It's alternating series, and we have n times x to the n. Oh, sorry, let me do it this way. So here, the center is 2. If x is equal to 2, then x minus 2 is equal to 0. So this series will converge. Every series converges at its center. All of them do. Our job is to see if we can expand that and have more possible x values. So we go to the ratio test. Absolute value signs. Take this and turn it upside down. So we'll have 1 over n times x minus 2 to the n. And over here, I have 1. Well, I need to write that a little bit bigger. Hang on. Let me give myself enough room. There. All right, I hope you can see all that okay. And now a whole bunch of stuff's going to cancel out. All right. The n and the n plus 1 cancel out. As n goes to infinity, that plus 1 just doesn't mean anything at all. So they disappear, they become a 1. And what we're going to be left with is, we're just going to be left with x minus 2. Everything else cancels out. All right. So you're always left with an x to the first. In this case, we got this minus 2 on here. And what we need that to be less than 1. We need the absolute value of that to be less than 1. So that means -1 has to do this, +1. We solve this little equation here. We're going to add 2 to both sides. So if we add 2, we get 1. And 2, we get x. And 2, we get 3. Is that? Wait a minute. Hold on a minute. Something's not quite. I messed up somewhere. Hang on a minute. Where did I mess up? I made a mistake somewhere. I can't see what I did. Hold on. Huh. Something doesn't quite look right to me, but let's find out what happens here. So we need -1 has to be x minus 2, 1. So taking off the absolute value signs, to be less than 1 means we have to be bigger than -1 or smaller than +1. Now we add 2 everywhere to solve this. So if we add 2, we get this. X, we get 3. Okay, so there's the interval of convergence. And what's exactly in the middle of 1 and 3? What number is right in the middle of 1 and 3? Which is the center, 2. So it really is the center here. Okay, so now we know, oh, this is going to work out. Yeah, this is going to work out. So now I'm going to draw this picture. So 1 and 3. So far we know this. And right here is the center. So far we know that between these two numbers, we will converge. Outside this interval, we will diverge. So if x is bigger than 3, we diverge. If x is less than 1, we diverge. If x is between 1 and 3, we converge, which leaves us with a finite radius And so now, we have to figure out what happens at those two endpoints. And before I do that, I'm just going to pause and see if anybody has a question. It's a lot to take in, isn't it? But this is all the good stuff. All right, so we look at the endpoints. So I'm going to go to this other board. Here's our series. So first we'll look at the left endpoint of x equals 1. So I'm going to put that in here. So that will give us, whoops, -1 to the n, 1 minus 2 to the n, and that will give me 0, -1 to the n, and 1 minus 2 is -1 to the n. So that's always, this is always going to be +1 because these are odd and even at the same time. So this is just going to give us this series of just 1 to the n, which is 1 plus 1 plus 1 plus 1, and that diverges. Oh, Brandon, I'm missing a 1 where? Where am I missing a 1? Oh, yeah, thank you. You're right. It's n x minus 2. Thank you. So that gives me this. That gives me n times -1 to the n. And so there's an n here. There we go. So this is all just going to turn into n, and that diverges. Thanks, Brandon. This just becomes 0 plus 1 plus 2 plus 3 plus 4 plus 5 plus 6. It just keeps getting bigger and bigger. So that diverges. Thanks, Brandon. I forgot to put that in there. All right, so that was the left endpoint. Now we go to the right endpoint. And the right endpoint is 3. So if I put 3 in here, we get 3 minus 1 is 2. So we get 1 to the n. But that just turns out, so 1 to the n is just 1. So that gives us this. So we get this series, -1 to the n. So this is going to be 0, minus 1, plus 2, minus 3, plus 4. And this also, that also diverges. Even though it's an alternating series, the terms are getting bigger. So this diverges. So the answer to this question is, answer to this problem is, we diverge at both endpoints. So that's the picture of the answer right there. So these take some practice. I'm only going to send out about 3 or 4 homework problems tonight. We'll go into a little bit more on Thursday. I encourage you heavily to look at the examples in the book. I'm only going to give you like 3 or 4 homework problems tonight because Tuesday to Thursday is not a long time to do all this stuff. So you got the recording, go visit Isaac. All right, he can help out with a bunch of this stuff as well. All right. Questions about anything? Probably feels a little overwhelming at this point, but you'll get okay at these. Right? So if you practiced all the ratio test stuff, it's just got this extra bit of an X showing up in there. And I gave you some examples of where this shows up in the real world, and we'll see more of that in a little bit. All right, anybody got any questions? Can we just go over the canceling again on this one? How I got, oh, so Brandon, X minus 2 came in the original problem. That's part of the original series. This thing, maybe I'm not understanding your question right. Oh, how I got X minus 2 in the canceling. Oh, yeah. Hang on a second. Did I erase all that? Yeah, of course I did. Hang on. So where the canceling came from. Yeah, I went through that a little bit on the quick side. So when we go to the ratio test, we get the limit as n goes to infinity. So when we're doing the ratio test, marker's going bad. So there's the ratio test. What I'm doing when I write it is I'm skipping this, and I'm doing this. Are you okay with these two are the same thing? Okay, because yeah, just dividing. So over here we get n times x minus, oh, sorry. So we add 1 to all the x's, to all the n's. So we get n plus 1, x minus 2 to the n plus 1. And then it's just over 1 because there's no denominator over here. And then times, turn this upside down. So this becomes 1 over n, x minus 2 to the n. All right, so you good up to there? All right, now, if we look just at this, there's exactly one more of these on the top than on the bottom. Yeah, I know you see it now. So there's my x minus 2, because this one and this one, they cancel out and leave me with that. And then n plus 1 over n, as n goes to infinity, this just turns into the number 1 because that constant. So we're just left with that. And then we get minus 1, and that's where I got it. But you see that now, right? Yeah, it's a good question to ask. Good question to ask. You're welcome. All right. Stop the recording here at this point. So I'm only going to send out a few homework questions, like 3 or 4 or something.